my name is Manish Gupta, and this is video number 203. In this video, I'm going to talk about GPTQ, which is a method for accurate post-training quantization for GPT models, generative pre-trained transformer models. So let's get started. How does GPTQ work, right? So GPTQ is basically a quantization method. And why do we need quantization? Well, if we do not do quantization, then let's say if we take a model GPT-3, which has 175 billion parameters, that basically takes up 326 GB kind of space to store weights in float 16 format, right? So this is a lot, and therefore we need some sort of quantization. Now, the good part about GPTQ is that it can help you quantize such kind of large models like GPT-3 175 billion in around 4 GPU hours, reducing to 3 to 4 bits with very small accuracy degradation, right? So in quantization, of course, the main idea is to reduce the number of bits used to store every weight. So GPTQ can actually reduce the number of weights to just 3 or 4 bits while just spending about 4 GPU hours on a A100 for 175 billion parameter models with very little change in the accuracy, right? So of course, for any kind of quantization, there can be two ways of quantizing while training or quantizing after training is done. So GPTQ basically believes in post-training quantization, which is quantizing after the training is done. Okay. Also, while quantizing, you could basically do quantization over the entire model, all the weights together, or do it layer by layer. Of course, layer by layer is better. So therefore, GPTQ actually does layer-wise post-training quantization. Okay. Now, in quantization, the basic goal is that if you have a particular layer, of course, the particular layer typically computes y equal to wx, where x is the input, w is the set of weights. What you want to do is to quantize your weights w to 3 or 4 bits such that you get w hat and such that your reconstruction error is as small as possible, right? So essentially, that's how you basically get your w hat, which is the quantized set of weights. Now, to do this very efficiently, people have proposed something called as optimal brain quantization, which is not GPTQ, which is basically a way of doing this, doing this minimization of reconstruction error in an efficient manner. Okay. But we'll see how GPTQ improves on that. But before we understand how GPTQ improves on this basic way of doing quantization called optimal brain quantization, we first need to understand how this OBQ method actually works. Okay. So in fact, in this method, what is shown is that if you want to quantize this entire weight matrix W, you can actually quantize it row by row. So this optimization that you see here can actually be done by minimizing the sum of squared errors over each row of W. Okay. So you basically try to quantize it row by row, which basically means that yes, you can handle the row W independently of other rows. And you can quantize one weight at a time in every row, right? So basically, first of all, you can split this optimization problem into row-wise optimization problems. And each row of W, right? And that basically means, and for each row-wise optimization problems, what you could do is to quantize one weight at a time. Okay. Of course, you will choose at any point of time, if your W basically is R cross C, R row C columns. So, for every row, you're first going to choose which of the C weights you're going to quantize, right? By some criteria right here, right? And then after you've chosen that particular weight that has to be quantized, you quantize that guy, but you also change the other weights so as to adjust for the error that this quantization incurs. Okay. So therefore, what this OBQ method does, this method is called OBQ. What this method does is basically to handle each row row of the weight matrix independently, and it quantizes one weight at a time while updating all not yet quantized weights to compensate for the error. Now, how does it basically choose, the weight to be quantized? Well, basically it uses this formula. So essentially it chooses that qth weight to be quantized, per row, by finding that weight, which leads to, first of all, minimum quantization error. So when you're quantizing, you basically try to take the weight and round it to the nearest value on the quantization grid, right? And you typically have quantization grid. So if you have like 4 bits, you have like 2:4 different levels. So that defines your grid, minimum and maximum for that bin. And then you try to quantize it to the nearest value. Now, So basically, which weight do you choose? You choose that weight which leads to minimum quantization error as well as minimum increase in the loss. Okay, as well as minimum increase in the loss if you basically quantize this weight. Okay, so remember, if you basically quantize any weight, you may actually incur some change in the loss, overall final loss that is to be optimized, right? Now, to be able to figure out this minimum change in loss, people typically use the Hessian matrix. So change is basically derivative and Hessian is second level derivative, right? So basically, by bringing in this Hessian, I'm not going to go into too much of math, but by bringing in this Hessian, what you're trying to do is to ensure that when you remove this weight, you cause minimum loss in your minimum increase in the loss in your objective finally. Not removing the weight, I mean quantizing the weight, right? So that's that. Now, after you've quantized this particular weight, you of course need to change other weights. So in the same row, of course, remember these are row-wise optimization problems. So you have to basically take those set of F set of weights, which are the remaining full precision non-quantized weights. You basically try to sort of use this formula and essentially update those weights so that they can make up for the loss because of the quantization of this WQ guy. Okay. So in summary, what OBQ method does is basically thinks about this quantization of the weight matrix problem row by row and quantizes element by element. So one weight value at a time, right? While doing this quantization, of course, there is this H inverse matrix which is involved, the Hessian, right? And the inverse of the Hessian. Now remember, if your weight matrix is R cross C, your Hessian matrix is basically going to be R cross C cross R cross C. That Hessian matrix is a very large matrix. Okay. So, and the idea is when you basically remove or rather quantize a particular weight, your Hessian needs to be updated, right? So therefore, this H inverse, if not done appropriately, can be very, very inefficient. So therefore, what OBQ method proposes is a very, very efficient method which avoids this expensive H inverse recomputation. I'm not really going to bring in all that math here, but by using Gaussian elimination, they remove the qth row and the qth column of H and thereby update the Hessian for every change in the in the WQ that you do. For every WQ quantization that you do, they basically update the Hessian, right? They don't recompute the Hessian from the scratch, right? So which basically means that OBQ is really efficient. It basically, although its runtime really looks very high, RC cube, but remember it is still pretty efficient rather than recomputing H inverse from scratch every time. Okay. So, and broadly, of course, OBQ actually picks WQ with the least quantization error and the minimum change in the minimum increase in the loss. Okay. Okay. Now, can we do better is the question that GPTQ folks asked, right? So the first question to ask is, if I look at any row in the weight matrix, OBQ basically just chooses a particular weight. It can be any randomly ordered weight. So it basically chooses that particular weight, which sort of leads to minimum quantization error and minimum increase in the loss, right? What happens if I quantize weights in arbitrary order, right? So if I basically don't depend on this particular order of choosing the weights, what if I basically just, quantize weights in arbitrary order? And particularly OBQ is interested in choosing the same order for all the rows. I mean, remember there are so many row-wise optimization problems to be solved. So OBQ actually quantizes rows of W differently. So in the first row, it could quantize, let's say the 10th weight and then the first weight and then the 100th weight and so on. But GPTQ basically says, let me quantize weights of all rows in the same order, and that too basically the start to end order. Quantize the first weight, quantize the second weight, third weight, fourth weight, fifth weight for every row. So do that for the first row, second row, third row, everything. Okay. So in other words, what GPTQ proposes is that I'll basically go column by column. I'll basically quantize the first column for all the rows, second column for all the rows, third column for all the rows, and so on. Now, why go column by column? Because the point is that the set of unquantized weights F is basically the same for all the rows, right? So remember, if I choose to quantize the first weight, all the other weights in the row are in the set F. Similarly, if I quantize the second weight, all the remaining, third to the end of column, end of row are the weights which are in this unquantized set F. Okay. Which basically means that if I go column by column, I can use the same HF inverse. Okay. So remember when I'm using HF, so H, the Hessian is very big, R cross C cross R cross C, right? And when I'm trying to solve these row by row problems, I'm actually looking at a block in this Hessian matrix, in this large Hessian matrix, right? So the idea is that when you do this, when you update the weights in a particular order for every row. And so what happens is that your set of unquantized weights remains the same. And similarly, your HF inverse is also the same for all the rows. Okay. So remember, the Hessian basically depends only on the layer inputs. So it only depends on the X part. Of course, its derivative with respect to the set of weights which are remaining. Okay. So therefore, the idea is in GPTQ is that for every row you use the same order, and therefore actually what is useful is to actually quantize column by column. Okay. Now doing this column by column basically means that you need to update your Hessian weight matrix not for every weight that you remove, but or you quantize, but only C times. Only C times, only the number of column times in your weight matrix. Okay. So this basically reduces the complexity of the overall method. It makes it much, much faster. Okay. Now, that's good. So you have made the method very, very fast theoretically, but practically does it become fast is the question. So, theoretically, we are basically saying that, yes, I mean, I don't need to update the Hessian R into C times. I would rather just update it, total C times. But, it turns out that the updates are not enough. Or rather, the frequency of updates is too fast, right? So the idea is the algorithm has a low compute to memory access ratio. So the idea is that these updates are still happening too fast, right? So if the weight matrix has, let's say, 10,000 columns, for every column you're going to go to the memory, and then you want to update the memory, right? So, and memory access is slow, compute is much faster, right? So therefore, what you want to do is to batch these updates if possible. So what GPTQ further does is to essentially, rather than updating at every step the entire huge matrix, it basically makes use of this interesting property that when you're trying to update this Hessian and when you're trying to do quantization, you only care about values in that particular column. So the rounding decisions by quantization depend only on the updates performed on this column I only. And therefore, you can batch updates for various columns. So what they do is basically, not just that you don't update the Hessian for every weight quantization, R into C weight quantizations. So on the previous slide, we already saw that you update only C times. But can you actually even reduce this to basically do this C divided by B times, where B is a batch size? I mean, basically you update the Hessian only, after you've looked at 128 different columns. So the idea is that, given a particular weight matrix, you essentially do quantization, of course, column by column, but you update the Hessian only after you've looked at, let's say, 128 columns in the weight matrix. Now that makes it super fast. It basically ensures a very good, healthy compute to memory access ratios, so that the compute is not waiting too much, or rather is not blocked so many times by memory accesses. Okay. So you do global updates of the entire Hessian matrix and W after a block is processed, after you process a block of weights. Okay. So the overall algorithm, but then, there's one other third thing, I already talked about first. Basically, GPTQ does the Hessian updates after only C times rather than R into C times, right? Second, it does lazy batch updates, so it doesn't really even do C times. So this was the first. This is the second optimization. Basically, it does batch of columns together. Third thing that it does is rather than actually doing updates to the Hessian, it basically does updates to the Cholesky reformulation of the Hessian. Now, again, I'm not really going to get into the math of it, but the point is that for nice, interesting mathematical properties, it's better to express Hessian in the Cholesky reformulation. So it therefore does updates to the Cholesky reformulation directly rather than original Hessian matrix itself. Okay. So the overall algorithm works as follows. You basically have the input weights W, and you also have the Hessian, which can be computed for the entire. You compute Hessian in the beginning, so that takes quite some time, but you compute the Hessian and Hessian inverse in the beginning, right? You also have a block size B to indicate how many columns do you batch together for the Hessian updates, right? So your Q is basically going to be your final quantized weights, right? Your E is basically D row cross B. So that's basically the block quantization errors, how much error is happening when you are trying to quantize this block, okay? your Hessian inverse was already computed. You apply Cholesky reformulation, you get the Cholesky reformulated Hessian matrix, right? And then for every batch, you're basically within every batch, you're basically going to quantize a column of the weights. I mean, of course, you keep a track of the error also so that you can update the weights in this block. And then after the entire block has been processed, you actually update the remaining weights. Update the remaining weights and also the Hessian in that sense is update the remaining weights and the Hessian. So you see the updation of the remaining weights and the Hessian actually happens only C divided by B times, which makes GPTQ very fast, right? So now, here is a comparison of how GPTQ performs compared to the other usual quantization method, which is round to nearest method. So people have compared across two different families of GPT models, OPT and Bloom, right? And on the x-axis is the size of the model, y-axis is the perplexity. So lower the perplexity, the better the model is, right? So as you observe, the FP16 model, of course, has the lowest perplexity, the dotted black line, because it is 16-bit, it's not quantized. And the quantization is doing 4-bit quantization, which basically means there will be loss in perplexity, or rather there will be increased perplexity, as you would observe, right? As you observe, RTN or round to nearest method is pretty unstable. So for certain regimes of model size, it can actually have very high perplexity, which is bad. While GPTQ basically gives you much stable perplexity, much closer to the 16-bit model as your model size increases. Okay. Now, so this is also observed here. So essentially, this is on Wikitext2, and you basically have the perplexity values comparing the full model, the 16-bit model, to the round to nearest and the GPTQ optimized models for 4-bit optimization, 4-bit quantization, and 3-bit quantization for different model sizes, right, all the way up to 175 billion parameters. So as you see, the perplexity here is 8.34, while with GPTQ, the perplexity is 8.37, very close to 8.34, not too bad, right? Even with 3 bits, it actually does not really go too bad. It just increases to 8.68, okay? So that's that. Now, and the similar kind of story you can observe for the Bloom model also, again, all the way up to the 176 billion parameter model. Now, compared to RTN, you see the Bloom's perplexity is lower, which is better, right? So the Bloom's perplexity is lower, which is better. RTN can actually sometimes go very wild and have very high perplexity values. Yeah. Now, compared to, comparing the runtime, so if you look at OPT 175 billion parameter model, or even look at other sizes, 13 billion, 30 billion, 175 billion, it takes about 4.2 hours for 175 billion model to be GPTQ quantized for a 800 GPU machine. Similarly, for the Bloom model, 176 billion parameter Bloom model, it takes about 3.8 hours. So it basically just takes 4 hours approximately for quantization of these large models on an 800 machine without much increase in perplexity values. Lastly, you can also quantize them over little lower grade machines like A6000 machines. So the interesting part is if you basically want to do inferences, right, with the FP16 kind of quantized FP16 model, it basically takes 230 milliseconds. However, if you basically care about a 3-bit quantized model, essentially it gives you like 71 milliseconds as the you see the inference latency, which basically means that there is a speedup of 3.24x. So high speedup without much loss in accuracy, and it basically allows you inference. So because of this quantized model, you can of course do batching nicely. And therefore, the interesting part is that you can actually do this inference of the 175 billion parameter model on a single GPU. So on a single GPU, you can actually get the inference in 71 milliseconds on an 800 machine compared to actually otherwise getting it on 5 GPUs in 230 milliseconds. Now, isn't that sweet? So therefore, GPTQ is awesome. It enables you to deploy these large models on single GPU machines with higher throughput, with low inference latency, and therefore higher throughputs. Okay. So in summary, in this video, I talked about GPTQ, which is an approximate second-order method. It basically depends on Hessian. So it's a second-order method for quantizing large language models. It does layer-wise post-quantization, and you can quantize up to 3 to 4 bits without really much loss in downstream accuracy. as measured by perplexity, as I showed already on the slides. More results are in the paper on other downstream tasks and also other benchmark data sets, right? So in short, GPTQ can lead to significant end-to-end speedups, both in terms of inference latencies and also reduces the model size significantly so that you can batch more of you can batch more of instances on the same machine, enabling you to do fast inferences using fast inferences on models as large as 175 billion parameters, right, on a single A100 GPU, right? Okay, that's it. So that's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.